We usually think of fabrics as passive things, right? Clothes just sit there, curtains block light.
Yeah, totally passive.
But what if they could do something? Like, what if the very clothes you're wearing could generate warmth on a chilly day?
Ah, that's where things get really interesting. Seeing these everyday materials being re-engineered with really clever functionality built in, it's fascinating.
Exactly. And today we're doing a deep dive into one of these innovations, fabrics with built-in heating. We've got our hands on an academic article. It's called Hybrid Fabrics for Ohmic Heating Applications.
Right.
And we're going to try and figure out how they make this cozy magic happen.
Yeah, our goal is really to explore the science, how these fabrics heat up, look at where this tech might take us, and just appreciate the clever engineering behind it all.
But without getting totally bogged down in the super technical jargon.
Exactly. Keep it understandable.
Okay, so the big question first. What exactly are ohmic heating fabrics?
Okay, so in simple terms, they're textiles specifically designed to produce heat when an electric current runs through them.
Okay.
It's based on a principle called Joule heating. Think of the element in your toaster.
Ah, yeah. Gets hot when electricity flows.
Precisely. It's a similar idea, just, woven into a fabric.
So you could genuinely have a jacket that warms you up at the flick of a switch. That sounds incredibly useful, especially for those days when the weather just can't decide what it's doing.
Exactly. And the potential uses are pretty broad. The article points to personal thermal management, helping us adapt to changing temperatures.
Right.
But also medical treatments like electrotherapy, where controlled warmth can actually be therapeutic.
That makes a lot of sense. But I mean, a fabric that heats up also needs to be practical, doesn't it? It can't just be warm for 5 minutes and then, fall apart or feel awful.
Oh, absolutely. That's crucial. The researchers really stress that these fabrics need to be corrosion resistant, breathable, super important for comfort so you don't get clammy.
Yeah.
Durable enough to handle washing, and of course they need to generate heat consistently and efficiently.
Okay. And what's the key ingredient in this specific fabric they studied? What makes it work?
So this particular fabric is what they call a hybrid. It's a mix.
A mix?
Yeah, a mix of different fibers. It's mostly polyester and cotton for the, normal fabric feel and comfort.
Yeah.
But it also has a small amount of stainless steel staple fibers. They're sold under the name Bekinox.
Stainless steel.
Yeah.
In fabric. Wow. That sounds kind of stiff. Maybe uncomfortable.
You'd think so, right? But actually, these Bekinox fibers are incredibly fine. We're talking 8 micrometers in diameter.
8 micrometers. How small is that really?
Much, much thinner than a human hair. And they're about 45 millimeters long. Because they're so fine, they can be blended right into the yarn without making the fabric feel rough or scratchy at all.
Okay, that makes more sense. Paints a much more comfortable picture. So these tiny steel fibers, they're the conductors. They do the heating.
Exactly. Stainless steel conducts electricity. These Bekinox fibers, they're alloys, mostly iron, but with nickel and chromium too.
Gotcha.
They get mixed in with the polyester and cotton when the yarn is actually spun. And what's quite remarkable is the amount. It's only about 10% by weight.
Just 10%?
Yeah, which sounds like maybe a lot, but by volume, it's only about 2%. And that tiny amount is enough to give the whole fabric its electrical heating properties.
Wow. So a little goes a long way there.
Yeah.
The article also mentioned they looked closely at the surface of these fibers. What did they find?
They did. The analysis showed basically a mix of the metals themselves, iron, nickel, chromium, but also their oxides on the surface.
Oxides? Like rust, but for stainless steel.
Sort of, yeah. It's important because it helps understand how stable these fibers might be over time, with washing and wear, and how that surface might affect their electrical behavior.
Right. Okay, this brings up a question for me.
Right.
Why go through all the trouble of using these superfine, specific metal fibers blended in? Why not just, weave in regular thin metal wires?
That's a really good question. And the answer is, it's actually quite hard to make metal fibers that thin, especially getting below, say, 100 micrometers in diameter.
Oh, really?
Yeah, it often needs specialized manufacturing techniques, not like making standard electrical wire.
So it's a production challenge mainly.
That's a big part of it. And there are other approaches people try, like coating plastic fibers with metal or applying conductive coatings onto regular textile fibers.
Okay.
The article also briefly mentions conductive polymers as another route.
Conductive polymers.
Mm-hmm.
Plastics that conduct electricity. That sounds pretty high-tech.
They are, and they have their own unique electrical properties, different from metals and semiconductors. But, for making comfortable clothing, things that feel like normal fabric and can be processed on standard textile machines,
Yeah.
these hybrid yarns, the ones with just a small bit of fine metal fiber, seem to offer really good balance. You get the conductivity you need, but you keep the comfort and processability.
Okay, right, that makes sense. So we've got these special yarns, conductive fibers mixed in. Now, how does the heating actually happen? Let's get into the ohmic heating part.
Okay, so at its core, the principle is pretty straightforward. When electricity flows through something that resists its flow.
Like these fibers.
Exactly. When it encounters resistance, that electrical energy gets converted into heat. That's Joule heating. Simple as that, really.
Oh, right, like my old physics classes. Like a resistor warming up.
Precisely. You probably remember Ohm's law, V equals IR.
Vaguely. Voltage equals current times resistance.
That's the one. Now, for most simple metal conductors, like a copper wire, the resistance changes pretty predictably with temperature. Usually it increases a bit as it gets hotter, often in a fairly linear way.
Okay, predictably. But I'm guessing from the article, this hybrid fabric doesn't behave so predictably.
You guessed right. That's a key finding. The study showed that the electrical behavior of this polyester cotton steel blend was, well, more complex. And importantly, it was nonlinear.
Nonlinear, so not a straight line on the graph.
Exactly. It didn't follow that simple Ohm's law relationship. The resistance wasn't constant.
Huh. Why not? What's making it behave differently?
The researchers think it's mostly down to all the points where those short individual stainless steel fibers touch each other within the yarn.
Ah, the interfaces.
Yes. Unlike a continuous wire where current has a clear path, here the electricity has to effectively jump or bridge these tiny contact points between fibers.
So it's less like a highway.
Yeah.
And more like a complex network of tiny roads and junctions.
That's a great analogy, yes. And this makes it challenging to predict exactly how the fabric will behave using those simple traditional models based just on Ohm's law. They don't quite cut it.
Okay, so the math gets a bit trickier.
It does. They observed this nonlinearity in the current voltage curves, confirming the resistance isn't fixed. It changes in a more complex way depending on the voltage applied.
And the article mentions something called contact resistance. What's that about?
Right, contact resistance. That's the specific electrical resistance that arises right at the points where the conductive fibers physically touch.
Okay.
And it's affected by lots of things. How rough or smooth the fiber surfaces are, if they're clean or have insulating oxide layers, how much force is pressing them together within the yarn and the fabric structure.
That makes sense. If the connection isn't great, it's harder for the electricity to get through, more resistance.
Exactly. And while you might picture a woven fabric as maybe a neat grid of resistors where the threads cross, in these hybrid fabrics made with short staple fibers, the contacts are much more random.
Random.
Yeah, they occur all along the length of the fibers within the yarn, not just neatly at the weave intersections. It's a more tangled, conductive network.
So much less predictable than a simple grid.
Precisely. And the experiments they did really highlighted this complexity. One key thing they observed was hysteresis.
Hysteresis. Okay, that sounds familiar, but refresh my memory.
Sure. Think of it like this. They ramped up the voltage across the fabric and measured the current. Then they ramped the voltage back down.
Okay.
But the current didn't follow the exact same path on the way down as it did on the way up. There was a lag or a sort of memory effect. The fabric's electrical state depended on its recent history.
Whoa. So its resistance right now isn't just about the voltage right now, but also about what the voltage was doing just before.
Yeah.
That's weird for a simple heater.
It is unexpected if you're thinking of a basic resistor. They also found the electrical behavior wasn't uniform, wasn't homogeneous across the sample. Measuring resistance at different electric field strengths gave different results.
So different parts of the fabric conduct differently.
It suggests that, yeah, the conductivity isn't perfectly even throughout the material.
And what about distance? Did it matter how far apart they put the electrical contacts?
Oh, absolutely. This was a really significant finding. They found that as they increased the distance between the electrodes, the current flowing through the fabric dropped off almost exponentially.
Exponentially, not just linearly.
No, exponentially. Which means the resistance increased exponentially with distance, too.
That's a very sharp change.
It is, and it's quite different from what those simple grid models predict. They'd suggest more of a logarithmic relationship, much more gradual. So this really drives home how intricate these internal conductive pathways must be.
Okay, wow. So we have this fabric, it heats up, but its electrical side is, let's say, non-trivial, a bit quirky. How do they even figure out how hot it's going to get with all that complexity?
Right, good question. That's where physics comes in again, specifically the Stefan-Boltzmann law.
Okay.
This law describes how objects radiate thermal energy heat just because they're warm. The researchers use this law to connect the electrical power going into the fabric to the resulting surface temperature.
So it's like an energy balance. Electrical power in equals heat radiating out?
Essentially, yes. They had to account for things like the Stefan-Boltzmann constant, that's just a number from physics, the emissivity of polyester, which describes how well it radiates heat, and the fabric's surface area. But here's another interesting bit. They introduced something called an effective surface extension factor.
Effective surface extension factor?
Yeah.
Sounds complicated. What does it mean?
Well, think about it. A fabric isn't a smooth, flat sheet. It's made of countless tiny fibers.
It's textured.
Exactly. So the actual surface area that's available to radiate heat away is much, much larger than just the simple length times width area. All those tiny fiber surfaces add up.
Ah, I see. Like cooling fins, but microscopic.
Kind of, yeah. The study estimated this extension factor, which they called KS, was around 5 for this fabric, meaning the effective surface area for shedding heat was about 5 times larger than the basic geometric area.
That makes a huge difference in how quickly it cools down or how hot it gets for a given power.
It does, but even with that, was the heating perfectly even across the fabric surface?
Good question. Was it?
Not quite. They used thermal imaging cameras, the kind that show heat. And they observed some noticeable temperature variations. Hotter spots and cooler spots across the fabric sample.
Okay. And why would there be hotter spots?
The most likely reason is that those hotter areas correspond to places within the fabric that just happen to have a slightly higher electrical resistance.
Ah, so maybe fewer stainless steel fibers right there. Or maybe the connections between them aren't as good in that spot.
Precisely. Maybe a slightly lower density of the conductive fibers or less effective contact points. So more resistance means more heat generated right there, according to Joule's law.
So even in one piece of fabric, that random network we talked about isn't perfectly consistent everywhere.
That seems to be the case. And, this isn't just an academic point. It has real practical considerations.
Like what?
Well, imagine you're blending this heating fabric with other fibers. Maybe something like polypropylene, which can melt or get damaged at relatively low temperatures compared to polyester or cotton. You'd need to make sure that even the hottest spots on the heating fabric don't get hot enough to damage those other more sensitive fibers in the blend. You need to design for the peaks, not just the average.
That makes perfect sense. So, okay, let's try and wrap this up. These hybrid fabrics, the ones with the Becanox stainless steel fibers, they can definitely generate heat through ohmic heating. Opens up cool possibilities.
Absolutely. Wearable heating, therapeutic devices, lots of potential.
But, and this is the key takeaway from the article, it seems, their electrical behavior isn't simple. It's complex, it's nonlinear, doesn't quite follow Ohm's law perfectly.
Exactly. It's all down to the details, how those tiny conductive fibers are arranged, how they touch, the quality of those microscopic connections. That contact resistance and the random network structure are crucial.
And finding that sweet spot, that balance between getting enough conductivity for heating, but keeping it comfortable, flexible, durable, that's the engineering challenge.
That's the game. And what's really fascinating, I think, is how looking closely at these seemingly small details, the fiber interfaces, the randomness, the nonlinear effects, is what allows us to potentially create truly smart textiles.
Yeah. It makes you think, doesn't it? If this relatively simple-sounding hybrid fabric holds these hidden complexities, what other surprising behaviors might be lurking inside other materials we think are simple, behaviors we could maybe understand and then harness for completely new technologies in the future, beyond just heating, maybe sensing, reacting.
Precisely. What else is hiding in plain sight, just waiting for us to look closely enough? That's the exciting frontier.